Another method that we have to make alcohols is from the reduction of carbonyl compounds. And carbonyl compounds, we will have obviously that functional group. We can have ketones, and we can also have aldehydes, we can have esters, we can have carboxylic acids, etc. And we have for the reduction of alcohols, what is that? We are going to change the oxidation state of a carbon. But bottom line, what the reduction reaction does is add hydrogens across the double bond. So one method of doing that is simply a hydrogenation reaction. Let me do a molecule that actually contains an alkene and a ketone. If you use the hydrogenation, in catalytic hydrogenation, you could do with platinum, palladium, or you can also use nickel. Problem with that is that it's not selective. You need to use high pressures. And it will also hydrogenate alkenes and alkynes even. So if you did that condition, you are going to get the following. Yes, you will add hydrogen here and here across that, and you will make that alcohol, but you will also hydrogenate the alkene. So if you had in your molecule those functional groups together, then you cannot use the hydrogenation. And then there is other methods that actually are more selected towards carbonyl compounds. That is, they will not reduce alkenes or alkynes. And so for that, we have hydrides. First, we have one reagent is sodium boron hydride. What is interesting about this reagent is that it's not so reactive. We can handle that under, say, conditions with product solvent. We can use product solvents such as methanol or ethanol or even water, because even though it reacts with those product solvents to actually form hydrogen gas, destroying the reagent, but it does it slowly. It's slower than it's the reaction with the carbonyl. So we can use that in the presence of a product solvent. One thing important, again, is not so reactive, but it's also selective, because it's not so reactive precisely, to reduce aldehydes. Let's put an R here, and ketones, R prime. The third reagent that we're going to consider here is much stronger and is lithium aluminum hydride. That is very reactive. And because it's so reactive, it will react very fast with product solvents. So we cannot use it in the presence of any of that. It needs to be used under a hydrous condition. So those reactions need to be carried out in 2 steps. Step 1, doing the reduction. Step 2, add water. So again, I'm gonna say 3.1, and then 3.2, you add water to that. Not before, because you will destroy the lithium aluminum hydride, and that reaction is now faster than that. But what is interesting about lithium aluminum hydride, and I'm gonna erase the structure here. So lithium aluminum hydride, being more reactive, can be used to reduce other functional groups. It can reduce carboxylic acid and esters, besides reducing aldehydes and ketones. So again, if you want something that will only reduce aldehydes and ketones, sodium boron hydride is a good choice. However, if you want to reduce, besides that, if you want to reduce esters or even carboxylic acid, then you would use lithium aluminum hydride. But remember, that is in 2 steps. Reagent 3.1. Let's say first the hydride under anhydrous conditions, and then second you add the water. So that will be the summary of methods that we can use to reduce alcohols. And here I'm gonna just draw the mechanism for one of them. And mechanistically speaking, it is the same. It's a transfer of a hydride. And this is what happens. So if we have, say that I have aluminum here in my 4 hydrides, that's a formal negative charge. We have lithium just as the counter ion. So in that reaction, let's erase something here to have more room. Okay, so if I have a carbonyl compound, and as we said, this is very reactive, so never mind what carbonyl compound we're using. Here, my example has a ketone. What happens is that a hydride will be transferred over here. And so you are creating the following intermediate of that reaction. So you will be adding an H here, that's your hydride, and you will form an alkoxide. I'm not drawing the hydrogen, that's picture. And you need a second step, water, to add that hydrogen over here. But again, you're making an alcohol. And what are you doing? Reducing a ketone. What do we say that's a reduction? So now, what I'm gonna do is just give you the oxidation states. I have another video about oxidation states if you want to review it. But quickly here, let's go over the oxidation state change. When we go, for example, from the ketone that I have here to the final alcohol. That's my product. And I'm going to do the oxidation state here. Remember, when we do oxidation states, we are going to consider the difference in electronegativity to assign the electrons on the bond. When we do formal charge, the electrons in the bond are split even, say. But when we're doing oxidation state, we're going to take into account the difference in electronegativity to assign electrons. So now, when you're doing this carbon over here, we start always in those calculations with the number of valence electrons, and then you're going to subtract the electrons that are actually assigned to that particular atom. How do we do that? Okay, we say here there is no difference in electronegativity. So assigning electrons, you do split even, 1 and 1. Here, you also do 1 and 1. But now there is a difference in electronegativity between carbon and oxygen. So you will assign the 4 electrons to the oxygen. So now we count how many electrons are assigned to actually the central carbon. And we have none here, but here we have 1 and 2. So 4 minus 2 is a plus 2 oxidation state at the ketone. Now let's do the same thing over to this molecule. And now I need to draw the hydrogen that I didn't draw before to assign all the electrons in the bonds. So here you're starting again with 4 valence electrons. And now what you're doing is assigning what is in the structure assigned to that central carbon, taking into account difference in electronegativity. So between carbon and carbon is 1 for each. Here again, 1 for each. Now, carbon is more electronegative than hydrogen, so we'll take this through. But here the 2 electrons are assigned to the oxygen. Bottom line, how many electrons do we have assigned to that carbon? Now we have 1, 2, 3, and 4. So that's 0 oxidation state. So the oxidation state had gone from +2 to 0. That is a reduction. So this is just summarizing that. We have seen 3 main, conditions to do reduction of carbonyls. One was the hydrogenation, catalytic hydrogenation. The second one's using sodium borohydride. That can be used with product solvents. And the fourth reagent that we saw was lithium aluminumhydride. And we explained what is the difference between reactivity of these two and when should they be used.